And so this is the block diagram of 8051, or at least the classic 8051. New ones are called 8051 compatible, and their architecture is going to look slightly different, but overall it's the same theme. Okay, so what do you have? Well, you have the CPU or CPU core, which is in the middle on the left, right, middle left part. That's just a small little component of it. Most of the chip actually is devoted to everything else, including interrupt control, oscillator, on-chip ROM, bus control, on-chip RAM, GPIO, timer, serial port, and all that. And the fat arrows are really this internal bus that connect all these things together. Now, to talk about 8051, you first have to understand the memory spaces that it defines, or the instruction set architecture defines. So there are several spaces, roughly divided into what's called code space, the I data for internal data, and X data for external data. So there's at least these three spaces. At least that's how I like to view things. So code is for program memory as well as constant data. So for example, if you have strings, like hello world, the string, that's a constant, that's usually stored in code memory as well, even though it's not executable. IData or internal data memory, that's a small space. That's only 256 bytes, whereas code memory is up to 64K bytes. Okay, big difference. And Xdata is another 64K bytes for external data. Now, I think I mentioned this before. Xdata, that's only external to the core or external to the CPU, but oftentimes it's integrated on the same chip. The classical 8051 has a separate Xdata because memory chips were not easy to integrate back then, but now process technology has improved so much that it's just a tiny little area. So the 64K code and 64K of Xdata are conceptually separate. Okay, so even though they're both 64K, they usually refer to entirely separate locations. So if you have address 20, well, you have to tell me, are you talking about code data, code address 20 or Xdata address 20? If I don't know, I can't tell you the data. I can't access that. Okay, and so code is for instruction and constant data, including strings. IData mainly for the CPU registers, hardware stack, and maybe some global variables, some relatively small variables. And that's occupying half of the internal data or IData space. The other half, that is 128 bytes of that space, is for special function registers or SFR. And we're going to be talking about SFRs over and over and over and over and again. So remember, SFR stands for special function register. Okay? And SFRs are critical to how most microcontrollers work. Every microcontroller for embedded application has some kind of SFRs. Okay? And they might be in similar form like this or might be memory mapped, but they are still SFRs or special function registers. SFRs cause things to happen. Cause you to turn on a light, turn off a light, send a byte on the serial port to receive something, right? So these are all done through SFRs. So remember, SFR for special function registers. Now, Xdata can be used for software stack, main memory, global, whatever you want. Okay. But if you want to use Xdata as your stack, then you have to manage that stack pointer yourself, rather than relying on instruction to push and pop for you. If you have to use push and pop instructions, those operate on internal data space only. Okay, now 8051 registers. Well, so the term register is overloaded. It means actually different kinds of things depending on what you're talking about. But most people kind of use the term register loosely. So you have to be a little careful. Now, so if I don't say anything. If I just say register, a lot of times I actually refer to what they call general purpose registers, and specifically R0, R1, R2 through R7. So there are 8 of these that are what most people refer to as registers or general purpose registers or CPU registers. Now, there are others that can also be called registers, but they are slightly specialized. So there's something called A, or sometimes ACC. They refer to the same physical thing, but there's actually different representations for them. So that stands for accumulator. And we'll see some examples of how accumulators are used. Now, not every processor architecture uses accumulator. 8051 is one of them that actually uses accumulator. And it's a fun way to write a program. I actually like it. And for code generation, it's also interesting to use. Now, there's A, of course, uses and expects B. Okay, now that's another 8-bit register, but it's one of the special function registers. It doesn't really cause any input-output action to happen, but it's specialized for certain instructions. So for certain instructions like multiply and divide, you have no choice but to use B register in conjunction with A. That's just a restriction that's imposed by this instruction set. Now, most registers are 8 bits, but there are a few that are 16-bit registers. And you can't always access them directly. One of them is called DPTR, or data pointer. And that is a 16-bit pointer used for accessing either code memory or external data memory. Okay, and you can access the individual parts of the DPTR because it's 16 bits. But to get to the individual, you can divide that into the lower 8 bits and upper 8 bits. And so there's DPH and DPL. As you probably guessed, DPH for the data pointer high byte and data pointer low byte. And together, they form DPTR. So you can change the high byte or low byte individually, or you can access the whole thing as 16 bits. Now, so that's one of the special cases. Now, there's also PC for program counter. Now, you can't really directly set the program counter, but you can affect it kind of in a special way using like jump instruction or return instruction that causes the program counter to be loaded with particular address that you want, and that's where you're running, right? It points to the current instruction that you're executing. That's what a program counter is. There's something called PSW, or program status word, and that includes a number of bits that indicate the status, whether or not you have an overflow, or you have a carry, something wrong happened. Okay, so that's what PSW is, and we'll go over some of the details in a little bit. Okay, so now let's take a look at CPU registers, or R0 through R7. Now, there are 8 of them, right? So that means to pick one of them, it takes 3 bits, right? 2 to the power of 3 is 8. And so, and these 3 bits are usually found inside your instruction we might call the instruction encoding. And so it actually can encode instructions very tightly using just a few bits. Now, what 8051 does is you actually have up to 4 banks of registers. What does that mean? That means even though you refer to registers as R0 through R7, there's actually different sets of registers. You pick one set at a time, or one bank at a time. And these are actually mapped to the first 32 locations in your iData memory. Okay, so your internal data memory 0 corresponds to register R0 of bank 0. So bank 0 goes from address 0 through 7. Bank 1 from address 8 through 15. Bank 2 from 16 to 23. Bank 3 from 24 to 31. Okay? And so you could always get to the data location using the address I talked about. Now, but that takes 8 bits because you're just treating it as memory, right? 256 locations. But if you're using an instruction that refers to a register, then you can pick only 1 out of 8. But which 1 out of 8? Well, so it depends on the bank selection. And the bank selection depends on the setting in your processor status word. Okay, and we'll show you some details later. Now, accumulator is interesting in that it's an implicit register as part of many instructions. And in fact, it's both a source and a destination. So for example, there's an add instruction. And it has the format of something like add, and then a, comma, and #23. Something like that. What does that mean? That means a gets a plus 23. Okay? So that's how 8051 does it for a lot of instructions. So it could be add, subtract, and then AND, OR, XOR, all those. And so A is used twice, both as one of the sources and as the destination, right? So A gets A plus something. This something could be a constant, could be another register, could be a memory location, could be something else, right? So, so this way, you can encode the instruction very tightly. Why? Because there's only one A. And you don't need to represent A using 3 bits, for example. I mean, you need 3 bits to represent a register, right? Because there are 8 of them. But A, there's only one A. So you don't even need any bits to represent A. It's part of your what's called opcode, right? So a little add instruction with a 23, that takes 2 bytes. And sometimes if you have like add with a register, that takes just 1 byte. And so this achieves very high code density compared to many other instruction set architectures. Another architecture that achieves high density or code density is Java virtual machine or Java bytecode. Now Java bytecode does things a little different in that it doesn't have accumulator, but it uses stack concept. So everything is popped off stack and then pushed back on, push back, pop, and all that. But 8051, it has registers and accumulators, but it can really encode things very tightly.